This is a part 2 of the review. If you missed the part 1, don't forget to check that. Now we will go straight to Theorem 2 of the paper. Theorem 2 states an interesting observation that if we choose orthogonal random samplings instead of Gaussian random samplings, the mean squared error is improved with some specific margin, which is the function of SM result. Here is the theorem 2. We can imagine that there are some exploitation of the Gaussian property in the proof. The proof of theorem 2 takes almost 6 pages in appendix, so I summarize the proof sketch. There are the introduction of beautiful functions in definition 1. Sm function can be expressed with the beautiful function. Interestingly, lemma 4 states that we can get an inequality comes from Legendre transform of a random variable. This is the critical clue to get theorem 2 eventually. Theorem 5 is based on the previous lemma 4 to show the orthogonality gives smaller probability tails, and Theorem 6 states the inequality on the MSE, which is actually corollary of Theorem 2. Theorem 2 follows immediately from this Theorem 6. The author says the beautiful function f can be expressed using expectation, where random variable w is sampled from a probabilistic isotropic distribution omega, and the scalar function g is an entire function with a non-negative power series coefficients. Notice that it is a general statement that we use exponential function as g, and the expectation on the right hand side exists as we discussed when we are saying about the approximation of Sm function. When you say why they call it beautiful, I have no clue, but it's mathematical beauty in the context of our purpose, the approximation of softmax kernel. If we take omega as the isotropic, the varied Gaussian distribution, and g is exponential function, which is obviously an anti-function, the Sm function can be defined using the beautiful function f of g. Again, it's just a general statement for our next move. Don't be afraid. Now we can think about two variants. The first one is random variables are samples from IID for the standard Monte Carlo estimator. The other one is not IID, but each sample is orthogonal to the other samples. A simple way to have those samples includes QL decomposition of a Gaussian random matrix and takes the vectors from the decomposed orthogonal matrix. Now we need a lemma 4 to proceed. It prepares an inequality that a tail probability is less than or equal to the exponential function with the function of all variables m, x, and a. Let's just start with Markov's inequality. The proof of Markov's inequality uses the definition of expectation in an integral form, an inequality from the change of the integrated region, and the variable inequality in the region. So the left-hand side of equation 40 can be expressed like this, but let us stick to their generalization with the Legendre transform, which gives a sharper bound. In large deviation theory, particularly with the central limit theorem, we can get the tail probability is less than or equal to the exponential function. Using the moment generating function m of z, the Legendre transformation is defined as this using the supremum. I believe the detail is out of scope and we don't need further for the rest of proof. Just one note is, if we sample using a large M, the probability goes to 0, or the upper bound approximates the trail probability for their flat shape of PDF in its tail. We can show that the tail probability of orthogonal sampling is shrinking, which means that the distribution of a beautiful function f is concentrated to the center, a desired property. Let's just start with the upper bound of lemma 4. I rearrange it with the definitions, and rearrangements get this. For the orthogonal samples, we can rearrange it like this. Remind that g is the exponential in this case. The infimum can be ignored in the inequality for any theta greater than 0. For the comparison between the expectation of exponential function with theta and the summation of random features, use the Taylor series for the exponential. The second line in equation 44 essentially uses the multinomial theorem. The coefficients c of j1 through jm is defined as j factorial over j1 factorial times through jm factorial. Therefore, we get the two comparative expectation of orthogonal samples and IID samples. We define the delta as the difference between the IIDs and orthogonals. Here, delta is positive. Let's see if why. Again, Taylor series for the exponential function. Unfortunately, I don't get equation 50. I think we missed some coefficients here. I believe some terms are missing in equation 50. I believe it's a typos. However, the delta hat is got through the last term. So I believe the equation 50 is not the exact formula, but it doesn't affect the rest of proof. We will use orthogonality to rewrite the equation. Remind that the definition of dot product which involves the degree between two vectors. A set of orthogonal vectors can be expressed with a randomly rotated set of m canonical basis vectors with the magnitudes of the orthogonal vectors. Here, the orthogonal vectors can have some magnitudes other than 1. We can get a new set of degrees which is rotated from canonical basis vectors for a fixed Gaussian vector, G. Now, the orthogonal vectors are chosen independently with respect to the expectation, so these are factorized into 3 parts. To take advantage of a simple form of canonical basis vectors, denote a vector G consists of a Gaussian scalar samples. Now we have this for the orthogonal case. Then how about the IID case? Here we use the independence of IID samples. Let's just see how the second line comes. Here, we don't need canonical basis vectors for IID samples, but for simplicity, we can use any fixed deterministic unit length vector. For the detail, please refer to the comment in the open review. In this way, we similarly get factorized terms except the last expectation term. Now we need lemma 5 to rewrite equation 55. Notice that the right-hand side of equation 57 is not from equation 56, just a similar one. Denote R, which consists of G and its independent copy. We have equation 58. Notice that R has the same distribution of direction with G and the same distribution of magnitudes of G, which is actually a chi distribution. Now, we see that equation 59 proves equation 57. Through lemma 5, we have the same numerator in equation 60 and 61 from the left and right side of delta hat, but we have different denominators. We will summarize using tau. Notice that equation 61 can get through a similar arrangement of lemma 5 with a beautiful thing with Gaussian distribution. Since the marginal distribution are the same, two comparative equations are the same except the last term, and we can rewrite using tau defined in equation 63. Remark 1. Since the odd moments of Gaussian's color distribution are zero, if one of the I is odd, then delta hat is 0. Remark 2. If all the i's are zeros except at most one, tau is 1, which makes delta hat is 0. In these cases, two cases trivially get the same results. Marked on another typos. Now we rewrite equation 50 and 46, marked on the another typos for expectation and suspiciously missing terms. Therefore, to complete the proof, it suffices to show that this condition. Let's check with the conditions. Previously, our mark 1 and 2 states above conditions. Negation of these states are quite tight conditions, but lemma 6 says that two even numbers suffice to show that result. Let's check with this result. Actually, equation 63 reminds us the chi distribution. If random variables follows the standard normal distribution, squared root of summation of squared variables follows the chi distribution. The row moments are given by the above equation. Using the definition of gamma function, we can get the upper bound. This is the rearrangements using the definitions. Since the i's are even, so let the I is 2, d prime I, and we assumed d is even or odd. If d is even, and of course the I is also even, each group in the blue dashes is less than or equal to 1, decreasing to the right. To maximize, we choose 2, di and dj are 2, while the others are zeros, following the condition of lemma 6. In the odd d case, a similar approach can give a similar result. So, with the condition of maximization, we get the upper bound of d over d plus 2. Therefore, we complete the proof of lemma 6. And consequently, the proof of Theorem 5. Theorem 6 states that there is a specific gap. The proof uses similar approaches used in the course of the proof of Theorem 5. Let's start with the expectation of standard Monte Carlo estimators with m samples. The next equation 70 and 71 uses multinomial theorem to expand. We can summarize the MSE differences as in equation 72. The next slides show how equation 72 comes. Here, the point is the rearrangement of the coefficients in multinomial theorem. Now we use the definition of entire functions and the similar analysis in the proof of Theorem 5 or 3. Using Lemma 6, we get this inequality. The blue box terms are the same. Using the equation 56 and 36, the blue box turned into f of g, which completes the proof. Finally, we have Theorem 2. We prove that the orthogonal samples improve the MSE where the margin is the function of m, d, and the squared result of for x and y. Here are the highlights in the proof of part 2. Lemma 4 gives an inequality for a tailed probability using Legendre transformation. Theorem 5 states the orthogonality provides smaller tails, where we use a trick with canonical basis vectors to prove this. Lemma 5 gives an insight on beautiful things with Gaussian distribution. Lemma 6 gives an upper bound on the analysis on chi distributions.